live chat. Alright, and now we have come to my least favorite part of this topic, which is geometric proofs. And the only reason for that is because it's really, really hard. In my HSC paper, I believe I got served a really hard geometric proof question in question 15, and I don't think I was able to do it, from what I remember. And it's geometric proof questions is just one of those questions where you really need to expose yourself. I mean, this goes for all of maths, but proofs especially, you need to actually just try to expose yourself to as many questions as humanly possible. Because you'll start picking up these little motifs that exist within, sorry to use English terms, that might have triggered people. You pick up these little motifs in proof questions that are actually important. Yeah, and as it says on the slide, the hardest part of proof questions is actually knowing when to apply a formula. So, and this only comes with practice and kind of making those neural links of like, I'm matching this pattern, I know what to use here, right? And yeah, always draw diagrams, super important. Okay, suppose that u and v are non-zero, non-parallel vectors in R3 of the same magnitude. Prove that u minus v is perpendicular to u plus v. Okay, I'm going to follow my own advice and draw a diagram. So u, v, u plus v is going to be, let's try a different color. U plus v is going to be this, and then u minus v will be it will be this. Yeah. Already what you will see is that what we've created is a parallelogram, and we've created u minus v and u plus v are diagonals of a parallelogram. I'm sure some of you have proved this question before in extension 1, because this is a pretty classic question, but this is in 3 dimensions, so you got to be careful about that. So u equals u1, u2, u3. Yeah. This naming scheme of using subscript to denote x, y, and z is pretty common, by the way. And v equals v1, v2, v3. Okay. Now, u minus v is equal to u1 minus v1, u2 minus v2, u3 minus v3. And u plus v is equal to u1 plus v1, u2 plus v2, u3 plus v3. Okay? Now, if these are perpendicular, then, so we are required to prove that u minus v dot product by u plus v that equals 0. That's what we have to prove. In fact, that's probably something you want to put at the top of a proof. So let's do that. So u1 minus v1, u2 minus v2, u3 minus v3, u1 plus v1, u2 plus v2, u3 plus v3. That equals, I want you guys to notice the perfect squares that are happening. So we're going to get u1 squared minus v1 squared plus u2 squared minus v2 squared plus u3 squared minus v3 squared. Okay, and let's collect the like terms. Well, not collect like terms, but let's group them together. So u1 squared plus u2 squared plus u3 squared minus v1 squared plus v2 squared plus v3 squared. Now, there should be alarm bells ringing in your head. What do these remind you of? What should remind you of is magnitude squared. So this is actually the same as magnitude squared of u minus magnitude squared of v. And we're given two vectors of equal magnitude. So this is the same as u squared minus u squared, which equals 0. And therefore perpendicular. Okay, that completes the proof. If you need any help with this, again, asking the live chat. Okay, the non-zero point A has the position vector A, B, C, and the vector OA makes angle alpha, beta, gamma with the x, y, z axes respectively. By taking the product with the three unit vectors I, j, and k, prove that cos squared alpha plus cos squared beta plus cos squared alpha equals 1. Okay, let's draw a diagram. Okay, so it's asking us to find this angle, this angle, it's asking us to find this angle, it's asking us to find this angle. Well, it's asking us to find relationships about those angles actually. Okay, if it's a bit hard to understand those angles when I'm drawing, I recommend searching up on YouTube or GeoGebra, you know, making finding angles on the positive axes. But you'll kind of understand more when I start working out the question. Okay, so let's get the positive x-axis out first. So the x-axis angle sorry. Okay, we know we find the angle by cos alpha equals a dot beta on alpha beta. And we've been given that we should use the unit vectors to find the angles, right? So if you actually went into this exam and you didn't know how to find the angle to the positive x-axis, then you would just kind of try to guess it using the fact that they've given it to you by taking the dot product with the three unit vectors I, J, and K. But you should really be going into this exam knowing that when you want to find an angle between a vector and the x-axis, you go A is obviously your position vector, so A is equal to A, B, C, and then your B here should be whatever axis you want to find. So if you want to find the x-axis, you should use 1, 0, 0, 0, 1, 0, or 0, 0, 1. Yeah? Okay, so this actually becomes A, B, C, 1, 0, 0 all over root a squared plus b squared plus c squared, which just becomes a on root a squared plus b squared plus c squared. Yep, that looks fine. And then similarly, I won't go through the entire working out for all these. You'll find that this will be b on a squared plus b squared plus c squared, and then the gamma will be a c on a squared plus b squared plus c squared. Okay, let's see if I can add a new page here. I can't, that's awesome. Okay, now we have that cos alpha equals a on blah blah blah, cos beta equals b on blah blah blah, cos gamma equals c on blah blah blah. Now cos squared alpha will equal a squared on a squared plus b squared plus c squared. Cos squared beta equals b squared on alpha, a squared plus b squared plus c squared. And cos squared gamma equals c squared on a squared plus b squared plus c squared. And then if you add all these together, cos squared alpha plus cos squared beta plus cos squared gamma, this will equal a squared plus b squared plus c squared all over a squared plus b squared plus c squared, which obviously becomes 1. And then we complete our proof. You can end your proofs with a square or a QED or with nothing. It doesn't really matter. I just like telling my markers that my proof has finished at a specific point, and I honestly urge you to do it as well because it's just good mathematical convention. Okay, Now, this is going to be an extended example. This, I believe, was a question 14 in one of the HSCs, so getting definitely a bit more difficult, and you might not be exactly ready to prove these questions right out of the box. Okay? You've just learned about geometry proofs, so I'm not expecting you to fully understand or fully grasp these concepts yet, but yeah, I wanted to include this just to further your understanding. Okay, first we need to show that AC equals n plus m. Okay. So we're required to prove that AC equals n on m plus n over b a. Yeah. So we should first note that AB, so this thing, is just b minus a. Yeah, because minus a would be like that. And then so b minus a. So b minus a. And then if we read the question, so the point C divides it into interval a, b, so that CB on AC equals b on m on n. So that means CB ratio AC is equal to m ratio n. Yeah, so we've actually been given how to divide these two up. So since AB equals b minus a, then the total will be m plus m. And for AC, it'll be n of m plus n times by AB. So this will be n on m plus m into b minus a. Okay, now we're also required to prove that OC equals m on m plus n a plus n on m plus n b. So OC is just going to be OA plus AC. So we found AC. OC required to prove that m on m plus n a. A quick tip is that if you see a 1 marker or a 2 marker, it should be pretty simple. So don't overcomplicate things. OC equals m plus n. Yep. So OC will be OA plus AC. So OA is obviously A, so it's going to be A plus n on m plus n, B minus A. And then that's going to be n on m plus nb plus A into 1 minus n on m plus n, which will just be n on m plus n b plus A into m plus n minus n on m plus n, which equals n on m plus n b plus m on m plus n a. And there you go. That's our result. Yep, so take those off. Okay. Now this is the second part of that same question. So usually the first part is usually Nessa giving us some freebie marks, and then the second part is like, let's differentiate the band 6 students and the band 5 students and the band 4 students. Let OPQR be a parallelogram with OP equals P and OR equals R. The point S is the midpoint of QR. Okay, so R to Q is going to be P, so R to S will be half P. I feel like that might be important, so let's write it down. And OR equals R, yeah. Show that OT equals 2 on 3 R plus 1 on 3 P. Okay, when you're confronted with a question, this is actually quite a difficult question. You're confronted with an interval that you don't know how to prove, but you are given intervals between other things. Yeah, so you know that OS equals R plus half P. Yeah, that means OT has to equal some scalar multiple of that. Yep, that's got lambda 1. And how else could we define OT? Well, we can define OT going through OP to PT. Yeah, so PR is going to be R minus P, and OR is going to be, sorry, PT will be sum lambda R minus P. And then OT will then be lambda 2 R plus lambda 2, sorry, plus P into 1 minus lambda 2. Yeah? So this one is coming from the addition of OP. Okay. Let's do this next part in the next question. So we've been given we've found two different ways to define OT. So we've got lambda 1 R plus lambda 1 on 2P. And we also have lambda 2R plus P into 1 minus lambda 2. So we've lambda 2, lambda 1. So since these two vectors are equal, we can just equate them. So lambda 1 equals lambda 2 because we've equated the R values. And then we can now equate the P values. So 1 minus lambda 2 equals lambda 1 on 2. Let's just replace that with lambda 1 since they're supposed to be equal. 1 equals 3 lambda 1 on 2. Lambda 1 equals 2 on 3. And then let's check what OT actually is. So OT will be 2 on 3 lambda plus 2 on 3 divided by 2P, which is the same as 2 on 3 R plus 1 on 3P. Have we proved it? Yes, we have. All right. You might think I just kind of pulled this out of nowhere, but again, this has been derived off of like years of experience dealing with these kind of proofs. Using parts 2 and 3 or otherwise, prove that T is the point that divides the interval PR into the ratio 2 to 1. Okay. The way I'm going to do this fourth part of the question is I'm going to find TS, and we know RS, so then I can find TR and then prove that TR is 1 out of 3 or 1/3 of PR, and then that will prove that it's in a ratio of 2 to 1. Yeah, so TS, so part 4. So again, just in case that wasn't clear enough, so we found OT and we know OS, so now we can find TS, right? And we already know RS. So using vector addition, we can find TR. Yeah, and all we have to do to prove that T divides the interval PR in a ratio of 2 to 1 is that TR should be 1/3 of PR and PT should be 2/3. Yeah, so TS will be OS minus OT, which is equal to R plus half P minus 2 on 3R minus 1 on 3P, which is equal to 1 on 3 R minus plus 1 on 6P. So that's TS, and then TR will be, so this is TS. TS. Actually, sorry, this should be the other way around. My apologies. So OT minus OS. OT minus OS. To find TS. You'd actually need to do OT. Sorry, this would have to be TO plus OS. Yes, TO plus OS. So TO is just a negative of OT. So actually I was correct before. So that's going to be negative 2 on 3 R minus 1 on 3 P plus, why do I type myself? R plus half P. That equals 1 on 3 R plus 1 on 6 P. So that's officially TS now. And then TS plus SR will equal TR, which is what we're trying to find. And then that will equal 1 on 3R plus 1 on 6P plus, sorry, minus a half P, which equals 1 on 3R minus 1 on 3P, which is the same as 1 on 3R minus P, which is the same as 1 on 3 PR. So yeah, we've just sufficiently proved that TR is a third of PR, and therefore T divides it into thirds, and the other section is 2/3. So yeah, you could write this more verbosely, but I'll leave that up to you guys. So that's proven. And if you actually want me to give a more extended proof of this, please ask in the live chat, and I'll finish off this proof a bit more extensively. So yeah, that was like an E4 question. So yeah, E4, E3, high E3 type question. So congrats if you got it. If you didn't, that's all good. This is another hard example that we'll go through. Again, don't throw it if you don't really understand how to do this question. It's not too important if you don't understand. So yeah. Okay. So, show that HA plus HP plus HT plus HT equals 0. Let's read the question first. The diagram shows the pyramid ABCDS where ABCD is a square. So, important to note this is a square. The diagonals of the sector of square bisect each other at H. Right? So, these are all right angles. Okay. These are all right angles. So show that HA plus HP plus HT plus HT equals 0. So by the factor of bisecting these diagonals, right? HA, I should do this here. HA is going to equal negative HC because it's the same magnitude but opposite direction. And HB equals negative HD. And then just subbing those in, you get HA plus HB minus HA minus HD, which equals 0. Cool. Let G be the point such that GA plus GB plus GC plus GD plus GS equals 0. Part 2 asks us to use part 1 and show that 4GH plus GS equals 0. Okay. An important skill in geometric proofs, or any proofs really, is to factor in the fact of any unchanging variables. So GS here does not change, if you can notice. So GS does not change. So let's try not to touch that in our proof, right? Sometimes it is touched and then reconstructed, but let's just try not to, right? And plus, we're using part 1. So in part 1, we found that HA plus HB plus HC plus HD equals 0. Yeah. Now, how can we redefine the left 4 elements of our new outcome, this thing? How can we redefine it to use this? Right? We could use vector properties. Yeah. So GA could become GH plus HA. Yeah. GB could become GH plus HB. GC could become GH plus HC, and GD can become GH plus HD. Okay, so adding all that together, that's going to become 4GH plus HA plus HB plus HC plus HD plus GS equals 0. This obviously equals 0 from our previous question. So 4GH plus GS equals 0. Okay. Now part 3 is a 1 marker. So again, let's try not to think too deeply about 1 markers. It should be fairly obvious how to think of it. So 4GH equals negative GS. Now we want to redefine GS to use HG and to use HS. So we could do GH minus, sorry, I'm going to do GH plus HS, which is the same as 4GH equals negative GH negative HS, which is 5GH equals negative HS. And then if we actually flipped GH to become HC, this would become negative 5HG equals negative HS. And then HS would be, so lambda would be found by dividing this over, and therefore lambda equals 1/5. Another really hard question, and definitely a question where you need to be exposed to these kind of tricky vector manipulation components to really be able to understand. I've tried not to prepare myself for these questions. I did do this question before, a few days ago, but I wanted to really come in and show authentically my thinking process. If still this isn't clear enough, or you want some further help, just leave a comment in the chat. All right, now to finish off, we're gonna solve a bunch of questions to really solidify your understanding. So this is going to be really helpful for you when you're revising for vectors. I'm just going to kind of go through my thought process. I actually haven't prepared for any of these questions. They should all be doable. But yeah, let's go. By equating components, consider the two lines in 3 dimensions given by r equals 3, negative 1, 7, plus lambda 1, 1, 2, 1, and r equals 3, negative 6, 2, plus lambda 2, negative 2, 1, 3. By equating components, find the point of the intersection between the 2 lines. All right, cool. So they told us to use components, and that is what I shall do. Y equals negative 1 plus 2 lambda 1. Z equals 7 plus lambda 1. X equals 3 minus 2 lambda 2. 6 lambda 2 equals 2 plus 3 lambda 2. Now we just equate these components. It seems like lambda will equal 0. Oh, sorry, not 0. Lambda 1 equals negative 2 lambda 2. Now so this is x. Now if we equate y, this will become negative 1 plus 2 lambda 1 equals negative 6 plus lambda 2. Subbing in this identity we just found, this will become negative 1 minus 4 lambda 2 equals negative 6 plus lambda 2. Which will be 5 equals 5 lambda 2, therefore lambda 2 equals 1, and lambda 1 equals negative 2. So now I'm just going to sub all this back in to find it. So sub it into either of them. I'm going to sub it into this one. 3 plus negative 2 is 1. Negative 1 minus 4 is negative 5. 7 minus 2 is 5. That is our intersection. Okay, that is a complex number question. Okay, what is the Cartesian equation of the line r equals 1, 3 plus lambda negative 2, 4? So x equals 1 minus 2 lambda, y equals 3 plus 4 lambda. I actually didn't go through how to find a Cartesian equation, but you're about to see now, so pay close attention. we want to separate everything to lambda, because that is when the functions are equal. So not the functions, the components are equal. So y minus 3 on 4 equals lambda, and then equate the two lambdas. So x minus 1 on 2, negative 2. X minus 1 on negative 2 equals y minus 3 on 4. 4x minus 4 equals negative 2y plus 6. And then we've got 2y plus 4x equals, did I mess something up? Plus 6, 4y minus 4. What did I mess up? 3 plus 4 lambda, y minus 3 on 4 equals lambda, or x minus 1 on negative 2. Oh, wait, no, I didn't mess up. Equals 10, and then we can just factor this out by, we can divide everything by 2. Y plus 2x equals 5, so it's going to be C. If you have any questions about that, leave a comment. We've got about 7 minutes left, so let's keep going. Let lambda 1 equal be the line of the equation xy equals negative 1, 7 plus lambda 3, 2. The line L2 passes through a negative 6, 5 and is parallel to L1. Find the equation of the line L2 in the form y equals mx plus c. So if a line is parallel to another, what does that mean in parametric form? It just means that the movement vectors are equal, right? So if line are parallel, then equal movement vectors. Okay, so we've been given a point that it passes through. So L2 is just going to be negative 6, 5 plus it's parallel, so 3, 2 lambda. Instead of calling it lambda, let's call it t, because it's not the same lambda. Okay, and then we want to find the Cartesian equation. So again, let's find our components. X plus 3 on 3 equals t. We want to find just the components again, equals t, and then equate them together. So x plus 6 on 3 equals y minus 5 on 2. Cross multiply. 2x plus 12 equals 3y minus 15. And then 3y equals 2x plus 27. And y equals 2 on 3x plus 9. Cool. Finally, the angle between A equals 204 and B equals negative 312, given the angle in degrees correct to one decimal place. I do not have a calculator with me right now, so I'll just give you the cosine of it. So the cosine is going to be A dot B dot AB. So that's going to be 204 dot negative 312 all over 2 squared plus 4 squared times by 3 squared plus 1 squared plus 2 squared. Should be negative 6 plus 8 on 4 plus 16, which is 20, times 9 plus 1 plus 4, which is 14. And then if you just do the inverse cos of that in your calculator, you should be able to find the answer. Okay, the distance between the points P negative 2, 4, 3 and 1 negative 2, 1 is 7 root 21, root 31 or 49. Just find the vector between them. So we're going to find PQ and then we're going to find its magnitude. So let's find PQ first. Which equals 3, negative 6, negative 2. And then the magnitude of that is going to be 3 squared plus 6 squared plus 2 squared. 9 plus 36 plus 4, which is going to be, what is it going to be? 49, which is 7. So it's going to be A. Okay, I'm happy to stop our lecture there. I really hope this lecture has been helpful for you. Just to summarize really quick what we've learned for today. We went through just a short revision on MX1, so mass extension 1 vector revision. We learned about dot product in 3D. We learned about parametric equations. And we learned about geometric proofs. I really hope that this lecture has helped you in a significant way to understanding these topics a bit better than your peers who didn't watch this lecture. And I really appreciate you guys taking out your time to watch this lecture, as it takes a lot of hard work from me to create them. So I'd like to thank you guys, and I hope you guys have a good rest of your holidays, and good luck to you in the HSC if you don't see my face again. Bye bye.